Morning, everybody.
Morning.
We'll go and start again and finish up 12.2. Today will be our last lesson, and then we'll start to review for the test on Friday. Starting tomorrow, we'll just do the chapter review. So you have 2 days for the chapter review, and then Friday, you can start the test. You can take the test anytime from Friday to Monday at midnight. Okay, so 12.2, the last thing to talk about today is the second law of thermodynamics. I talked about the first law yesterday, which says that energy cannot be created or destroyed. The second law says that entropy is always increasing in the universe. Or at least staying the same. So entropy is at least staying the same, if not increasing. You can never decrease entropy. So let's go ahead and define entropy. Entropy is basically a measure of how much disorder there is in a system. And there's a lot of ways to define entropy and define disorder, but one way to think of it would be just how messy something is. So if you have a room where things are all over the place and they're not put in a certain area, they're not organized, that's high entropy. If you have a room that's very organized, things are put away, that's low entropy. So disordered would be things scattered around, things not organized. Also, you can think of it as movement. So you would have higher entropy with higher movement. If you go from, say, a solid substance to a liquid to a gas, the entropy is increasing as you go to those states of matter.
So, Miss Polly,
Yes.
is that why? So, if entropy is movement and like the faster particles are moving, the warmer they get, is that why there's the whole thing with like climate change and everything heating up? Or is that totally unrelated?
Oh, yeah, that's a really good question. It definitely is part of that because, we use fossil fuels, right? We're burning things like propane, gasoline, oil. And when we burn those things, we are creating more entropy. And that goes in the atmosphere. So that certainly is true. Just by our burning fossil fuels, we make more entropy. Now, as far as the actual temperature change, entropy can be temperature change where it might not be. So you can scatter things around and increase entropy. So you can burn propane, and entropy is increasing because the propane molecules are going into the atmosphere. It's also a higher temperature, but that's unrelated. It's just because they're moving into the atmosphere. And over time, the energy disperses and it gets colder again. So climate change is possibly due to fossil fuels in the atmosphere that trap heat, like carbon dioxide and methane. So it's not so much that we're burning the things that causes the temperature change. It has to do with the gases that we have in the atmosphere that are like a blanket that trap the gases. So carbon dioxide and methane are good at keeping sunlight on the Earth's surface and heating it up that way.
Okay, that makes sense. Thank you.
That's a really good question, but actually over time, as entropy increases, the universe is going to lose heat energy. It's going to cool down over time, which might sound counterintuitive. But another way to think of entropy is that it's going from usable to unusable energy. And that's one way to think of it too, that the universe is going from usable energy to unusable energy. And over time, the universe is going to have energy scattered and dispersed all throughout to the point where it's not usable anymore.
Okay. Okay.
But it's a difficult concept, and there's a lot of things about it that are hard to define. But that's one way to think of it, as just things dispersing, things scattering, more disorder. And especially with solid, liquid, and gas, you can see that. You can think of solid particles as, people in a church pew. If you're sitting in a church pew, you're in a very ordered arrangement. You have a certain place to be. You can't really move out of that place very easily. So you're kind of locked in place. So that would be like a solid particle. Liquid, think of people walking through a crowd. And so they have more freedom to move around. They're not staying in one place. It's less ordered. And then you could think of gas as people bouncing off the walls. If you could imagine people bouncing off the walls like little bouncing balls at about 1,000 miles per hour, that's what gas would look like. And so it's very disordered. So that's why as you go from solid liquid to gas, you have higher entropy because you have more dispersal of molecules, you have more disorder. Also, if you have higher temperature, as we talked about, you have higher entropy. And it's for the same reason. You could imagine people walking through a crowd versus people running through a crowd. So if you have a crowd of people who are walking, it's more order than people who are running through a crowd. And that's how you can think of temperature change. So with more movement, you have more disorder. And that would involve both a phase change, going from solid to liquid, as well as temperature change. So write that here as well. Higher temperature means higher entropy. There's an equation for entropy too. We won't really use it in this chapter, but just for you to know what it is. Delta S equals Q over T, where delta S is entropy. And the units of entropy, sorry, I can't turn it off on my computer, so apologize. The units of entropy are joules over Kelvin. And then Q would be heat added to an object. And then T is temperature, always in Kelvin. So we can use this a lot to think about everyday examples of things that we just know work a certain way. We don't really think about it. If you have a room, empty room with air in it, the gas molecules are dispersed throughout it evenly. We take it for granted that the air is mixed evenly throughout the room and that in every space we could breathe in oxygen and be just fine. So that's how entropy works, where you have random dispersal, random movement of molecules that makes it uniform throughout an area. But there is a chance that if you were to be in a room, that all the oxygen would be in one corner of the room and you'd have no air anywhere else. Now, this never happens. We never have heard of this happening. We know that the room is always full of air, and that the air takes up all the space of the room that's evenly distributed through. But there is always a chance that the air molecules could randomly move to one area of the room. Now, why do they usually not do that? Because this is high entropy on this side. So if things are moved to one place, that's higher entropy than if they're scattered throughout. So the room with gas molecules that are scattered throughout has more entropy. I'm sorry, I wrote this wrong. I was thinking of high order. Erase the entropy part in there. That should be high order, low entropy. So we would call this low entropy, high order. And this would be high entropy, low order. So these molecules are more ordered because they're in one place compared to these ones that are scattered throughout. So why does this one happen more than this one? And that has to do with there being more possibilities of that happening. You know, if molecules are ordered in one area, that's a very low probability of that happening because there are so many other arrangements that could happen where you have molecules that are scattered throughout here. Let me give an example of this. Let me move my computer out of the way to show you a few demonstrations. Let's see if this works. I mentioned this to you last year in chemistry class. I don't remember if I did or not, but it's with the tea bags. I want to show you that. I also want to show you one other thing before I show you the tea bags. So I have right here Scrabble tiles. If you take random tiles and just dump them out and see what happens, and put the letters together, it makes nonsense. I mean, there's no words on here I can see at all. I don't know if you can see it on the screen or not, but it's just gibberish. And you'd actually would think it'd be pretty interesting and pretty random if you were to have that happen where you see an actual word or actual sentence. It doesn't happen too often where you dump out random tiles and you get, especially a sentence, might get a word or two, but to get a whole sentence that makes sense would be pretty unusual. And why is that? Because the chance of you having an intelligible sentence is very small compared to the possibilities of having unintelligible sentences. There are millions more examples of gibberish, things that don't make sense, than things that do make sense. And that's the same thing with the molecules in the air. They have a better chance of being scattered because there are more possibilities of that happening. Just like with the Scrabble tiles, making an intelligible word is very low probability compared to making gibberish. Okay, did I show this to you last year where you take out a tea bag, you open it up, you fold it over, and you light it on fire?
Oh, I think you did.
I don't know, did it work?
I don't remember. I vaguely remember this though.
No, we'll try it again.
Okay.
This is just a normal tea bag that I just emptied out the tea leaves. I just folded it over, and I light it on fire, and see what happens. Yeah, you can see that it just scatters and it's, the little particles are almost all gone. So the tea bag originally, I can show you one more tea bag. This was solid. So the particles are in one place. So this would be high order, low entropy because the particles are together. When I burn it now, I'm dispersing the particles. So I'm making this have high entropy and high disorder. So by heating something up, by burning something, I'm increasing the entropy in the surroundings. I'm going from usable energy to unusable energy. Now I could gather up every particle that was dispersed in the air, but that'd be very hard to do because they're all over the place now. They're all throughout my apartment. The particles that were in here, that were in one place, that's very ordered. But now the particles are in millions of different places all throughout my apartment. That's high disorder, high entropy. I think that's all I wanted to show you for demonstrations. So let me go back and I'll do 2 more notes and we'll end for today. My computer back on here. I mentioned before, you can think of entropy as usable versus unusable energy, and that you could say that entropy is going from usable to unusable energy. I'll write that on here too. So you might have heard of the energy crisis, or people are worried about getting energy in the future for powering cars, electricity. The reason for that, energy in the universe remains constant. From day one of creation till now, the energy in the universe has not changed at all. It's not increased or decreased. The energy crisis refers not to energy itself, but to usable energy. So over time, we're going from usable to unusable energy. Usable energy being like coal, for example. Heating up coal makes that coal go from usable energy in the form of coal to unusable energy in the form of heat and carbon dioxide and water vapor. And that's very hard to get back at that point. Theoretically, you could bring back the chemicals and remake coal, but it would be very hard to do. So energy, as it's dispersed through the atmosphere, is hard to get back. And at that point, you really can't get it back. So that's what we mean when we say entropy, is the ability to do work, the ability to do things that over time, it's hard to get back because the chemicals that were together are now dispersed throughout the atmosphere. Okay, that's it for the lesson today. Homework on page 331, just do 32, 33, and 34. Write them on here too. I can get this open. So do questions 32, 33, and 34 on page 331. And then tomorrow we'll do the chapter review. I'll write in here too in case you want to see the questions. And on Thursday will be the second half of the chapter review. And then you can take the test anytime from Friday to Monday. Then we'll start to review after that. So next week will be review week. You should get your final exam review either in the mail or delivered to you sometime this week. And we'll go through that all of next week.
Are you going to continue to have class every day next week?
Yes, I don't know about other teachers. Has anybody told you about if they want to meet on Zoom or what times they're talking about doing that?
I don't
Not
think
really.
so. Yeah.
But nobody said anything.
I mean, we've kind of talked about like trying to figure out a plan for reviewing and things like that, but we don't really have a set plan yet.
Okay. So Miss Zaleski has you on Thursday at 11, but besides that, I don't know of anybody else who has any Zoom meetings scheduled.
Miss Mahan now started having just the middle of last week, she started having Zoom meetings at 1 every day.
Okay, that's good to know.
Yeah.
Well, I mean, I guess for now, I'll just keep it at 11 unless things change. I mean, let me know if other teachers want to do things, but I haven't heard of anybody else wanting to have any kind of review meeting with you all. So we'll just plan on every day next week at 11, except on Thursday, which we'll have at 2:30. Because we have a Google Calendar set up for teachers to write down when they want to have a Zoom meeting, and nobody put anything down. So as far as I know, nobody wants to do anything. But we'll see what happens next week. That's okay. Do you have a question, Catherine? So you have your hand raised up.
Miss Holly, could you please go over the questions from yesterday really quick?
Sure.
Because I know they're going to be on the quiz, and I thought they were pretty easy, but then I was like, wait, maybe they're secretly really tricky. And
yeah, it's good to check to make sure you got the right answer. So for number 27, it says that the radiators heat up the surroundings and the steam condenses back into water. They're asking, how does it heat up the room? So for this one, the steam is going to give energy off to the surroundings. And as it does that, it's going to condense. So the steam loses energy, and when it loses energy, it will turn back into water and heat up the surroundings in the process.
okay, so if I said that Yeah, the steam condensed into water, giving off heat, heating the air.
Yeah,
That's
good. Mhm.
okay. Perfect.
And then for the next one, it was 20, oh, sorry, 30.
30? Yeah.
Okay, so for 30, it says that James Joule carefully measured the difference in temperature of water at the top and the bottom of the waterfall. Why do you expect a difference? So for that one, gravity is doing work on the water. So gravity is pulling the water down. And so work is being done on the water. It's giving energy to the water. So the water is gaining energy as it's moving down. The
Right.
energy is being transferred into heat energy. Some of it is, anyway.
Yeah. Okay.
So
So
go ahead.
yeah. So if I have that there's more energy or movement at the bottom of the waterfall, it's a higher temperature. So it's like, so it is a different temperature from at the top.
Exactly. Yeah. So at the bottom, it should be hotter because it's gained energy as it's moved down. It's converted energy into heat as it's done work.
Okay. That makes sense. Okay. And then just for number 31, I just have that the hammer smashing the lead is like it's working, exerting work on it. So then there's giving off thermal energy, which is increasing the temperature, heating it up.
Yeah, very good. Exactly.
Okay, perfect. And that's pretty much the quiz, just covers what you went over yesterday.
Those 3 questions. Yeah.
Okay. Okay, perfect. I think I'm going to go take that now then.
All right. Good luck.
Miss Holly, bye.
Have a good day.
Bye, Catherine. I probably won't get an answer, but that's okay. Okay. Have a good day, Miss Holly.
You too. Bye.